Welcome to True Projects. In this video, we are going to explain the project Safety Helmet Wearing Detection Model based on improved YOLO M. Introduction. The project focuses on enhancing workplace safety in the construction industry through the implementation of an intelligent safety helmet wearing detection system. With the widespread use of intelligent devices and advancements in deep learning, the project aims to leverage computer vision technology to monitor and ensure the proper usage of safety helmets by construction workers in real time. The construction environment poses significant risks, particularly the potential for injuries caused by falling objects. So, safety helmets play a crucial role in protecting workers from such hazards. But the traditional methods of manually supervising helmet usage are inefficient and resource intensive. So, this project addresses this challenge by employing deep learning algorithms for real time safety helmet detection, ensuring a more effective and automated safety monitoring process. So, the project employs state of the art deep learning techniques, particularly focusing on the YOLO, that is, you only look once architecture. Various iterations and improvements on YOLO, such as YOLO V3 and YOLO S, are explored to enhance the accuracy of safety helmet detection. The methodology involves modifications to the output dimensions, incorporation of new objective functions, and the utilization of lightweight networks like MobileNet V3 for improved computational efficiency. And the primary beneficiaries of this project are the workers in the construction industry whose safety is at risk due to the potential hazards of falling objects. By automating the detection of safety helmet usage, the project contributes to a safer working environment. Additionally, construction site managers and supervisors stand to benefit from the reduced need for manual monitoring, allowing them to allocate resources more efficiently and focus on other aspects of site management. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to develop a robust safety helmet detection system using computer vision and deep learning to automate the identification of workers without helmets, mitigating the risk of head injuries in construction sites. And we aim to introduce YOLO M, a customized version of YOLO V5S, optimized for safety helmet detection. And we explore and implement state of the art object detection algorithms, including YOLO variants, YOLO V5 Ghost CNN, SSD, RetinaNet, and FASTA RCNN. And the aim is to evaluate and compare the implemented safety helmet detection models based on precision, mean average precision, that is MAP, and recall metrics. Analyzing these metrics provides insights into the model's accuracy, overall performance, and ability to correctly identify positive samples. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is import required packages. So the initial step involves importing essential packages such as NumPy, Pandas, Matplotlib, sklearn, TensorFlow, and Keras. These form the foundational tools for data manipulation, visualization, and machine learning, creating a robust environment for subsequent tasks. The second step is exploring the dataset. So the dataset exploration phase encompasses reading and plotting images to gain an understanding of the data. The third step is image processing. So this step involves pre-processing images, including converting them to blob objects, defining classes, declaring bounding boxes, and converting arrays to NumPy arrays. These processes prepare the images for subsequent stages in the computer vision pipeline. The next step is loading the pre-trained model. Here, the pre-trained model is loaded and its network layers are read, output layers are extracted, setting the stage for utilizing the pre-trained model for object detection tasks. The next step is image processing again. So further image processing involves appending image annotation files, converting color spaces, creating masks, and resizing images. These steps ensure compatibility and optimization for the subsequent phases. The next step is data augmentation. So in this step, data augmentation techniques such as randomizing, rotating, and transforming images are applied. These augmentations enhance the model's ability to generalize and improve its performance on diverse datasets. The next step is installing packages for YOLO v5 in Colab. Here, the necessary packages for implementing YOLO v5 in Google Colab are installed, ensuring a seamless integration of the YOLO model for subsequent data processing and training. The next step is processing data based on YOLO v5 model. So, the data is pre-processed in alignment with the YOLO v5 model requirements in this step. This includes organizing and formatting the data to match the model's expectations, ensuring optimal training performance. The next step is training and building the model. In this step, YOLO V5S, YOLO M, YOLO V4, YOLO V3, YOLO V5 Ghost CNN, SSD, RetinaNet, and faster RCNN models are trained and built. This involves fine tuning the models on the specific dataset to improve object detection capabilities. And in the next step, as an extension, exploration of additional models such as YOLO V5/6 and V8 is conducted, aiming to enhance the robustness and accuracy of the final predictions beyond the initial set of models. And as an extension, again, a front end interface is constructed using the Flask framework and incorporating SQLite for user sign up and sign in functionalities. This user-friendly interface allows users to input images, triggering pre-processing and detection using the trained models. So after signing in, users input images through the front end, initiating the model detection process. So the given inputs undergo pre-processing. The pre-processed images are fed to trained models and the model infers and detects objects, applying segmentation and bounding boxes to identify and distinguish each object within the input images. And annotated images showcasing detected objects with bounding boxes are displayed through the front-end interface, providing users with a visual representation of the model's predictions. Now we'll understand about the algorithms used. So the first algorithm built is YOLO V5S, that is You Only Look Once version 5 small. So YOLO is an object detection algorithm that divides an image into a grid and predicts bounding boxes and class probabilities for each grid cell. YOLO V5S is a smaller variant designed for efficient and fast real-time object detection, making it suitable for applications with resource constraints. The next algorithm built is YOLO M, that is YOLO Mini. So YOLO M is a customized version derived from YOLO V5S, specifically tailored for safety helmet detection. It incorporates improvements such as lightweight backbone network, attention mechanisms, and multi-scale feature fusion to enhance accuracy and efficiency in identifying safety helmets. The next one is YOLO V4, that is You Only Look Once version 4. So YOLO V4 is an evolution of the YOLO series known for its improved accuracy and efficiency. It utilizes advanced features like CSP Darknet 53 as the backbone and PANnet for feature pyramid networks. YOLO V4 aims to provide state-of-the-art performance in object detection tasks. The next algorithm built is YOLO V3, that is You Only Look Once version 3. So YOLO V3 is an earlier version that introduced the concept of anchor boxes for bounding box prediction. It employs a Darknet 53 architecture and performs object detection in a single pass through the neural network. So YOLO V3 balances accuracy and speed in object detection tasks. The next algorithm built is YOLO V5 Ghost CNN, that is YOLO version 5 with GhostNet backbone. So YOLO V5 Ghost CNN incorporates the GhostNet backbone, a lightweight neural network designed for efficient computation. This variant aims to maintain accuracy while reducing model size, making it suitable for real-time applications. The next one is SSD, that is single shot multibox detector. So SSD is an object detection algorithm that uses a set of default bounding boxes with different aspect ratios to predict object locations. It employs multiple convolutional feature layers to capture object information at different scales, enabling accurate detection of objects of various sizes. The next one is RetinaNet. So RetinaNet introduces the focal loss to address the class imbalance issue in object detection. It utilizes a feature pyramid network to capture multi-scale features, and the focal loss prioritizes hard examples during training, improving accuracy, particularly for rare classes. And the last algorithm built is faster RCNN, that is faster region convolutional neural network. So FASTA RCNN is a two-stage object detection algorithm. It uses a region proposal network, that is RPN, to generate potential bounding box proposals, followed by a classifier to refine these proposals. This two-stage process enhances accuracy but may require more computational resources. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing precision scores of different algorithms. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, representing the ratio of true positives to the sum of true positives and false positives. This is recall scores comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall assesses the model's ability to capture relevant instances, calculated as the ratio of true positives to true positives and false negatives. And this is MAP scores comparison graph. In this graph on x-axis, I have MAP scores, that is mean average precision scores, and on y-axis I have algorithm names. So MAP evaluates object detection performance by calculating the average precision for each class and then determining the mean over all classes. So the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is the data folder in which I have required dataset. This is sample folder in which I have images on which we will make the detections. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code data in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And these are Python main code files. And this is notebook Jupyter source file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost and port unless configured differently. So this is the local host and this is the port. So now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if we are new users, we have to register first. Fill in all these details and click on register button to sign up. And if we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. So here we have to provide a credentials, username and password and click on login button. So it has redirected us to the detection page. So now we have to upload any image here and the application will detect the person's wearing helmet from the image. Click on choose file button. So from sample images folder, I'm selecting this image and click on open. So the image is loaded. Now click on upload button. So here we can see the application has detected the people and drawn a bounding box around them. And we can see a different color bounding box here labeled as helmet. So the application has detected and differentiated the person wearing helmet here. And we can also see a probability score beside label telling us how confident the application is about the detection. Click on back, we'll try again giving another image. Click on choose file button. This time I'm selecting this image and click on open so the image is loaded. Now click on upload button. So we can see the application has detected all the persons wearing helmet, and we can also see the probability score. Click on back, we'll try again. Click on choose file button. This time I'm uploading this image and click on open. The image is loaded. Now click on upload button. So we can see the persons wearing safety helmets and the person who is not wearing the safety helmet are detected and differentiated using different colored bounding boxes. And we can also see a probability score telling us the confidence level of the detection. So similarly, we can upload any image and can get the detections of the safety helmets. Now click on sign out. So the conclusion here is the project significantly contributes to workplace safety in the construction industry by developing an automated safety helmet detection system. Utilizing computer vision, the system enhances safety protocols, reducing the risk of head injuries through real-time monitoring of safety helmet compliance. And the implementation of cutting-edge algorithms including YOLO variants, customized YOLO M model, SSD, RetinaNet, and faster RCNN demonstrated a thorough exploration of safety helmet detection methodologies. The project's extension to explore additional algorithms like YOLO V5/6 and YOLO V8 contributed to the pursuit of more robust and accurate safety predictions. The integration of Flask with user authentication provides a user-friendly interface, enabled effective testing and validation of the developed safety helmet detection system. And the project's outcomes, ranging from algorithmic enhancements to practical Flask-based applications, offer a tangible contribution to the construction industry. By automating safety monitoring processes and providing an efficient detection system, the project aids construction site managers and workers in maintaining a safer working environment.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.